This is exercise 1.4.1. So this question says that in a space, in a linear vector space Vn, prove that the set of all vectors, what is the set? It's given by this. This set of all vectors orthogonal to any V, not equal to the null vector, forms a subspace Vn-1. So before we proceed, we need to look at some definitions. So first of all, we need to look at the definition of subspace. So a subspace is defined as follows. Given a vector space V, a subset of its elements that form a vector space themselves is called a subspace. So if we have a given linear vector space V, and from that if we select a particular subset of elements, and if that particular subset of elements also happens to form a linear vector space, then that particular subset of elements is called to be forming a subspace. Now there is a notation that we are using over here. We say this is the linear vector space, and if we write n as a superscript, then that n denotes dimensionality. So n is the dimensionality of the vector space V. So this is a notation that we are using. Now dimensionality is defined as the number of linearly independent basis vectors that we have. So this is another definition for dimensionality. Which says that a vector space has dimension n if it can accommodate a maximum of n linearly independent vectors. So this is the dimensionality. So if you have n linearly independent vectors, this n linearly independent vectors will form the n-dimensional basis for one n-dimensional vector space. So we have defined subspace and dimensionality. So let us proceed to solve this question. So as we see from the definition of dimensionality, we have that for an n-dimensional vector space, n-dimensional vector space, our given vector space Vn is n-dimensional, there will be n basis vectors. Basis vectors are what? Linearly independent vectors. So basis vectors means linearly independent. Which span that particular subspace. So for n-dimensional vector space Vn, we will have n linearly independent vectors forming the basis, and from the Gram-Schmidt orthonormalization, from Gram-Schmidt orthonormalization, we can obtain orthonormal basis vectors, which would again be n in number. So let us say that these n orthonormal vectors are denoted as follows. So the first vector we take, we can choose the first vector in the Gram-Schmidt process. So the first vector we will take and we will normalize it. So the first vector we consider here to be V, and since it is a basis vector, so for basis vectors, the basis needs to be non-zero. So linearly independent, non-zero. 0 cannot be a basis vector. So none of these vectors that we have written would be 0. So that means this V is also not equal to 0, and this is the first vector that we choose in the Gram-Schmidt process, and this is having unit magnitude. Then we will obtain the subsequent orthonormal vectors by the Gram-Schmidt orthonormalization process, and those orthonormal vectors we denote by this notation: V perpendicular 1, V perpendicular 2, so on and so forth, V perpendicular n minus 1. So since there can be only n linearly independent basis vectors for a vector space Vn of dimensionality n, and we have this V as one vector, so we will have remaining n minus 1 orthonormal linearly independent vectors which are non-zero. So now let us consider the following set. Consider the set that we want. This is the set of V perpendicular I, where I ranges from 1 to n minus 1. Both 1 and n minus 1 are included. So what is this? This is a set of n minus 1 orthonormal linearly independent vectors that we have. So this set will span, a space of n minus 1 dimensions. So since this set V perpendicular I is a set of linearly independent orthonormal vectors, this will be a set of basis vectors for a space of n minus 1 dimensions, because we have n minus 1 such linearly independent orthonormal vectors. So we have that the set where we have this set V perpendicular I, where I goes from, not 0 to n minus 1. I goes from 1 to n minus 1. This set spans a space having dimensionality of n minus 1. Now we need to show that this space is indeed a vector space. So this will be true. How will it be true? We will see right now. So if we consider linear combinations of V perpendicular I, we see that these linear combinations will be orthogonal to the vector V. Why so? So let us see why this is so. If we take V dot product or inner product with any other V perpendicular I, this will be 0. Why? Because we had obtained this set of linearly independent orthonormal vectors from the Gram-Schmidt orthonormalization. So from the Gram-Schmidt orthonormalization process guarantees that V perpendicular 1 is orthogonal to V, V perpendicular 2 is also orthogonal to V, V perpendicular n minus 1 is orthogonal to V. So each of these V perpendicular I's are orthogonal to V. So every such linear combination of V perpendicular I's will also be orthogonal to V. So we have this space in which each element is orthogonal to V. that means each of these linear combinations will be present in this space which is orthogonal to V. Also, for a linear vector space, we need the null vector. So, where and how will we find the null vector? So, we see that since V was not equal to 0 and none of these V perpendicular i's were equal to 0, but if we form linear combinations, so null vector will be obtained by linear combinations. And how is that? We will see, say for example, V plus I minus V plus I will be the null vector. Inverse, so minus V plus I is inverse of V plus I, and this is just a scalar multiple of V plus I, so it exists in this space spanned by V plus I. So we see that linear combinations of V plus I exist in this space spanned by V plus I. Null vector exists in this space spanned by V plus I. Also, the inverse of each vector exists in this space spanned by V plus I. Similarly, we can see for the other axioms. Thus, we can conclude that the set V plus I spans a vector space of dimensionality n-1, and since this set V plus I is a subset of Vn, therefore this set forms a subspace. Since it is a subset, since the elements are forming a set which is a subset of the elements of the vector space Vn, so we see that this given set indeed forms a subspace of the given vector space Vn. So we have and also the dimensionality is n-1. The dimensionality is n-1. So we have finally proved what we wanted to. We have shown that this particular set of orthogonal vectors to a given non-zero vector does indeed form a subspace of the original vector space that we started with.